to the webinar this morning, and thank you for your flexibility. And we're glad to be able to put something together for you folks this morning that specifically addresses gas and flame detection in your industry and within your company. My name is Jeff Russo with Gilson Engineering. I'm the MSA and General Monitors representative in Charleston, West Virginia. We have Dave Oppenheim, who's going to be presenting the webinar this morning. We have other people from the Gilson Engineering rep organization, Adriana Touche and Earl Morris from the MSA sales organization, as well as Steve Stotts from Houston. And then a number of TransCanada people. So at this point, I'm going to, before I turn it over to Dave, a couple of housekeeping things. We have everybody's microphone is muted, and a chat box over in the right-hand corner of your screen. In the upper right-hand corner, you'll see a chat icon. As questions arise during the presentation, if there's things you'd like to learn more about or have a question, type it into the chat box. We'll be looking at that chat box and we'll be breaking as appropriate to try to address those questions. The first half of the presentation is going to focus on flame detection, and then the second half hour will be gas detection. So there will be a logical break in between that we can try to wrap up questions on flame detection and so on and so forth. If we get a lot of questions, we may do what we can to answer a few at the break and then push the rest to the end. Just in the interest of time, we know that you all have other things on your calendar as well. So at this point, I want to introduce Dave Oppenheim. Dave is the Flame Detection Business Development Manager for General Monitors MSA, based in Minneapolis, Minnesota, with 32 years experience in the field in service, product management, sales management, and now as Business Development Manager for General Monitors MSA. And just so you know, and you can see it there on the slide, MSA purchased General Monitors a few years ago, so now they are all part of the same organization. However, we retain the MSA name and the General Monitors name in the marketplace for brand recognition. The products are somewhat segmented, but in other ways very similar, and I think in most, if not all cases, handled by the same rep network. So at this point, I will turn it over to Dave, and we hope you enjoy.
Thank you, Jeff. Good morning, everybody. Hope everyone is doing well on the call and is safe and sound. It's my pleasure to be here. We have got roughly 40 slides or so on fixed flame and gas detection. Here's the agenda. We'll follow it today. I'll have a quick safety minute. That's an MSA standard practice. We'll dive, as Jeff said, into flame detection to begin with. We'll do a high-level overview. We'll cover some more details on the model FL500 UVIR flame detector. We'll switch gears at that point and talk about combustible and toxic gas detection. I'll have a few slides on some interesting new technology developments on fixed gas. I'll address best practices on installation of fixed flame and gas, operations, and maintenance best practices, just at a high level. A slide on training, basically training topics around fixed flame and gas, and we'll be done. Sound okay? I hope so. And I wanted to mention, feel free to use that chat box for questions as they come through here. This is intended for you, our audience. We encourage your questions, your feedback, your thoughts, your comments. The best way to do it is to use that chat box. And like Jeff had mentioned, we'll take a 5-minute break between when I'm transitioning from flame detection to gas detection. We'll try to address some of those at that point, but otherwise you can hold off or on the end too. But in any event, I wanted to urge your comments and questions as we roll through this. So our safety minute today is on your smoke detectors at your home. They cut the risk, your risk and your family's risk of dying in a fire by 50%. So take care of these things. It's instrument management, right? at the season change, it's a great time to vacuum them, the dust if you have them, test them, replace the batteries if they're battery powered. Don't forget your CO monitors as well in your home. And if you have outbuildings with animals or pets, make sure that if you've got alarms there, you can hear them, and you're also managing and maintaining those detectors as well. So that's just again, hits home, close to home, and take care of your family and your pets. So optical flame detection technologies. The first sensor out there was an ultraviolet flame detector, and that actually was rolled out in the 60s, and it's actually saw a fire quite well. The problem was it also saw welding and lightning and all kinds of non-fire radiation sources. So our engineers coupled the Geiger-Müller UV photo tube along with a single frequency infrared sensor in the same electronic package. And by using a basic microprocessor running an AND gate signal processing logic, where the UV energy was of a sufficient energy level, and the infrared, which is part of a hydrocarbon fire emission signature, when you had both that UV and that IR present simultaneously with a field of view, this detector really augmented the false alarm rejection capability of that UV detector. And to this day, it's a fantastic technology, very strong. It detects a wide range of fuel types with generally fast response, because the signal processing is just an AND gate, where I have status 1 on UV, status 1 on IR. Now we've got a fire alarm. And but then in the early 2000s, with the rollout, or with the availability of 32-bit microprocessors, it was possible to measure basically 4 different wavelengths of infrared in the same instrument. And by using a more sophisticated algorithm, and ours is called NNT, or neural network technology, the bottom line is that this 4IR detector doubled the detection range, and still does, of the UVIR detector to the same size fire. So it does require, it is a hydrocarbon specific technology, meaning you can't use this for a hydrogen fire or a sulfur fire or a magnesium fire. But on hydrocarbon fires, so either liquid or gaseous, it basically doubles the range as compared to UVIR detectors. But they're not perfect, right? And the no detector is absolutely infallible or perfect. I'll talk about that coming up. But what a common characteristic they do share is they have a field of view. And I've actually got 2 views here on that field of view. One across the bottom is the view from the top of that area of coverage. A cone of vision is another way of describing it. And then the upper panel here shows that same information in 3-dimensional perspective. But let's focus on the bottom panel to begin with. In the left side of this lower panel of field of view comparisons, we've got the MSIR, the multi-spectrum IR. It's our model FL4000H, and the 100% basic label is the highest sensitivity setting. And this is all, by the way, I should have prefaced this. This is the detection coverage in response to a 1 foot by 1 foot square pan fire of heptane, which is the primary constituent of gasoline, right? So Factory Mutual used to use gasoline. Then they realized they had variability problems in the spring to the summer to the winter blend, and also geographically it was different. So heptane is a repeatable fuel, regardless of your location, and you can always, if you wanted to replicate these performance tests, you could, and because they're audited, you should be able to get the same results. But anyway, what I'm getting at here is 100% equals high sensitivity, 75% equals medium sensitivity setting on the device, 50% represents the lowest sensitivity. And so this is a comparison on the left of the multi-spectrum IR to that 1 by 1 heptane fire. On the far right is the model FL500 UVIR detector range to the same size fire. And you can see, sure enough, you know, the MSIR has a much longer range. And then in the middle is our previous generation UVIR detector called the FL3100H. And so with the FL500 coming out roughly a year and a half ago, 2 years ago, you can see how it leapfrogged the FL3100H in terms of its range and also its spread. The horizontal area of coverage actually on the FL3100, we were talking roughly 90 degrees, you know, maximum left to maximum right coverage. On the FL500, we're talking 130 degrees, so 55 degrees off center, left and right, so much broader field of view. And then again, the upper panel is the same data, but shown in a three-dimensional type of kind of perspective. Now, the next slide is going to talk about methane detection specifically. I don't have graphic images to show you on this, but it's important because I know our audience today is interested in primarily natural gas, and of course, methane being the primary component of natural gas. There's two options here in terms of defining the response of detectors to methane, and one is the more rigorous fire. That's the smaller fire, the 12-inch high methane plume fire, and that's used by Factory Mutual in their standard 3260 approval testing. When a manufacturer submits their devices to FM, they will test a 12-inch high methane plume fire. Now, an industry standard in some cases is an alternative standard is a 32-inch tall or high methane plume fire. Again, this is 2.5 times higher. So what it means is, and this is an option for every customer to consider, if I am going to expect a detection of a 12-inch high methane fire, then I'm going to get some detection range. And that's what I've got here. I just listed the MSIR detector first on both medium and high. And so to a 12-inch high plume fire, the MSIR can see that on the medium sensitivity of 50 feet on center, 80 feet on high sensitivity. And then our UVIR, 35 feet on center at medium and 50 feet on center on high sensitivity. So again, as I've mentioned, it's maybe not quite double here, but you can see that the FL4000 has more sensitivity to that fire size. Now, if we go to the 32-inch high methane plume fire, now we've got some greater distances because it's 2.5 times larger, 80 feet on center for your MSIR, 125 on center for your high, and FL500 60 and 80 medium and high respectively. So what's the takeaway here? Well, I'm going to talk about later on that too much sensitivity can be counterproductive in some cases, and we'll talk about why that is. So I wanted to first, though, just do a quick comparison head-to-head, strengths and limitations out of MSIR on the left, strengths and limitations of UVIR on the right. And so I'll just start with MSIR strengths. This is a hydrocarbon-only fire detector. I talked about that. Talked about the higher sensitivity, the extended field of view. It's optimal for large area monitoring. And where do we see these? We see these in aircraft hangars and in large warehouses and places where that field of view is a benefit. And maybe it can, with that extra range, can again cover the area with fewer devices in some cases. It's also a good option where the area is dirty and oily and just may not get cleaned as well because. And that translates also to a good option for sooty and smoky fires because those IR detectors actually have a higher resistance to optical blinding than a UV sensor does, but they're not impervious. And now on the weaknesses side of this, because that extra sensitivity is out there, you have to be careful in the aiming of it. And if there's a flare stack, if there's a heater, if there is a boiler or a reactor with a combustion process going on, the reality, you have to be careful in your aiming practice of that. And also, and this is true of any device on the market, any infrared detector, it can be blinded by water, ice, and snow. They absorb the infrared energy. They absorb the heat of a radiant flame. And that's just it's the same for all of them out there. And because these MSIR devices are looking at 4 signals and they're doing some fairly sophisticated processing, that they can require a little longer to create the alarm response in some cases, not all cases, but in some cases. Now moving to UVIR, here you've got a device that can see the hydrocarbon fires and it can be tuned to or set up by the manufacturer to sense hydrogen and sulfur. And even a magnesium fire. So non-hydrocarbon fires, it's got that capability as well. I showed you on the field of view comparison that wider field of view is optimal for shorter range, wider space coverage. You can actually maybe save the cost of one device in some cases if it's not a long range requirement on the coverage map. The alarm signal processing is a little faster because it's an AND gate. And now our device as well, and some of them out there too, and the others in the market, have a pre-alarm option. And where we have seen this useful for UV only is in transformer applications or electrostatics, where some sparking and arcing may actually be a precursor to an actual ignition. And so one transformer hall I was working on on the West Coast, they used that UV pre-alarm specifically to alert the techs on site that, hey man, we're having some sparking, we're seeing some energy that shouldn't be there, and the breakdown of insulation resistance is normally the root cause of that. And weaknesses on this device though, because you got two different sensor technologies, you have a combination of the contaminants. And so on the UV side, you know, silicones, dirt, and soot and oil and solvent vapors can all absorb UV to a degree. And then on the IR side, you have your water, ice, and snow. And then the last two bullets are just summarizing that if you have UV only energy in the field of view, well, now the device is satisfied on the UV side and it's essentially operating as an infrared only sensor. And likewise, if you have welding in the field of view, or IR, you have some heat, or then it's a UV only detector. So it just means that because of that more basic processing, it can, if you have that energy, you're halfway to a fire alarm in an AND gate type of device. But the bottom line is that they're both very world-class, both provide world-class performance. But in some applications where you don't need that longer range capability, MSA is recommending the UVIR as a suitable and basically the optimal technology. And so for Recip engines, where you're not looking for this long range capability, and extra sensitivity can actually be counterproductive in some cases, we like the model FL500 UVIR flame detector. And one of the benefits, or some of the benefits of it, is that it uses the same mounting bracket as the MSIR detector. It uses the same field wiring and conduit, uses the same handheld test lamp, and we can reuse or use the same site flame mapping as was used with the FL4000, provided it wasn't done on very high sensitivity. Baseline recommended sensitivity settings for this instrument on most projects or most compressor stations is the medium sensitivity setting, unless there is a need for longer range, 10-second time delay, and then hard enabled, of course, to allow the field techs to establish communication with the device on the 4 to 20, if that's being routed back to the an AI card on the PLC, and then they can talk to it in real time to look at diagnostics or whatever. And speaking of diagnostics, this device has got some nice features here. In addition to the HART protocol, for the routine walkthrough, the routine visual inspection, the three LEDs are really useful where green is good. Yellow would mean there's a trouble condition of some type. Normally it's a dirty window, but it could be low voltage or some other problem. And then if there's an alarm state, you have the red LED and obviously if it's on red, then there's something being detected at that point. As far as the installation piece, it's a nice modular design where you got a module on the inside. That's what the three images across the bottom represent. Pull the cover off, bring the cable wiring through. You can actually disconnect the Phoenix style green terminal connectors and make your wiring connections and plug them into the module, put the module back into the bulkhead or the base of the detector housing, and then thread the cover on. As far as mounting, from left to right, this is as an ex-field guy, I like to see a solid mounting structure, right? I mean, these detectors, both the multi-spectrum and the UVIR, the IR sides use modulation or flicker as part of their signal processing requirement or the algorithm, and that's because hydrocarbon fires breathe, and you can really see it with your kerosene, your diesel fuels, your crude oil fires, where that flame actually breathes, and it actually comes up and it makes a big cloud, then it releases, and that's like a 5 hertz flicker on those heavy liquid fuels. But even a methane or propane, they have a flicker rate as well. If you've got vibration, high level of vibration, your mounting structure, that's not good because it puts modulation into the device right off the bat before it's even seen a fire or seen a hot body. But they actually can withstand a fair amount of vibration, but excessive vibration is a problem. And there's some judgment there, but like I said, all things considered, the more solid you can make that, the better. Also want to see solid mounting fasteners. I was at a job site once where they use sheetrock screws to fix the mounting bracket to a wood wall, and it's like, guys, this is not adequate. You need solid fasteners. It's not that heavy, but you want something better than that. As far as the device itself, we like to see a slight downward angle. And in fact, as part of the commissioning process, and I've done this where I've been given a site coverage map, and I've got to go out and align the detectors to match the map, and that means both left to right, the horizontal axis aiming and then the vertical axis aiming. So again, we want a solid structure. We want a nice, I need flexible conduit. I was at a job site once where they had hard-walled the conduit into the device. It's like, guys, this is not going to allow us to align it. And then I like to see a termination box there, just in case we do have to move the thing or take it down for any reason. We've got the ability to work with that, a little more flexibility with a field termination J box nearby. And I just wanted to quickly show the FM, the factory mutual. This is the standard 3260 certificate of compliance, and it shows that the FM audited the performance claim by MSA, GMI, of the FL500, and this just shows you the field of view diagrams that they validated that we've got on high sensitivity to a 32-inch tall, methane plume. We get 80 feet on high, 60 feet on medium, and 45 feet on low. And so, again, we were talking about this, that again, as long as you're not looking for more than 80 feet of coverage, and in most cases 60 or even 45 is going to be adequate, we think that's a great place to start with this instrument for most applications. So I want to take a minute to just talk about the type of signal outputs from our flame detectors, and that's what the next slide here represents. So starting from the top, probably the most common signal outputs we see used in the field are fire alarm relays, and our devices and many in the market provide two. One is called instantaneous, or the warning relay, but its function is instantaneous. The minute it senses energy in excess of the alarm threshold setting, it energizes that instant relay, and so those contacts close. Then there's a second relay called timed or warning, but I like the word timed. Another term would be sustained. So so what that means is there's a programmable time delay function using a rocker switch in the device, and if you say 8 seconds, for example, then the fire has to be above the threshold setting for a continuous 8 seconds, and at that point, then the sustained or timed relay would energize, and those are both programmable in terms of normally energized or de-energized operation with no alarm state present, and then latching or non-latching contacts. The third relay is a trouble relay, and this is always normally energized with no trouble present, and that relay will de-energize on a trouble state, normally dirty windows, could be low power, or a loss of total power. So then it de-energizes when the device loses power. So it's a dual role device, a relay, I should say, trouble and loss of power. The fourth type of output is the analog 4 to 20 milliamp signal, and this is a step change only signal level, and I put some arrows here. So green is good, and that correlates to the device's green LED, and that means it's at 4 milliamps. And if it would have a dirty window, or what we call a Copham fault, then it would drop down to 3.5 milliamps, although we have options in the second and third column at 2 milliamps. If that was some clients have a standard analog level they like to use to indicate a specific type of fault, and we can do that a little more granularly with those levels. And then we have the alarm level, in this case at 16 milliamps, the instantaneous fire. So, and I like to put this out there for any new technicians or someone just not experienced with these flame detectors, and I ask this question to the audience: how is this different than a gas detector's analog signal? Well, that's what this slide represents, and I won't take long on this, but the vertical axis is our 4 to 20 milliamp signal, right, in milliamps, and so 4 we know is normal, and then on the horizontal axis is our percent of full scale. So if it's a LEL gas detector, sure enough, if the measured gas concentration in the measurement cavity is 50% of LEL, well, if you go up to the red line and go over, then we should see 12 milliamps out of our transmitter, right? Super easy to understand, and the logic solver will normally have threshold settings at 20% of scale and 40% of scale to equal a low alarm, enunciation device like a light, and then at 40% a high alarm enunciation device like a strobe or a horn, and our logic solver would energize those guys. Well, flame detector is different, and that's what the next slide puts into a graphic graphic state here. So same on the vertical, you get your 4 to 20 milliamp signal out of the transmitter, but on a horizontal, it's not. There's no indication of fire intensity. It's time, right? So if we just follow our little red graphic line here, from left to right, 4 milliamps, everything is good until the fire is detected. You see the little red arrow, and then boom, we have step change up to 16 milliamps. And at that point, when that analog value reaches 16 mils, the device energizes that instantaneous alarm relay, right? So that those two things happen at the same time, 16 milliamps and the warning or the instant relay energizes. Now, if we've got that 8-second time delay function set up like I mentioned, then as long as the energy being sensed by the device is sustained above that threshold for 8 seconds continuously, it'll continue off to the right until that 8 seconds timer is timed out, and boom, then the device output increases into step change to 20 milliamps, and then that reaching 20 milliamps correlates with the energizing of our sustained or timed alarm relay. At that point, the device has energized all its outputs other than trouble. And now I did want to mention down, if you go down to the table below, I put a box around the instant and the timed alarm relays, but you can see right above those two, there's an 8 milliamp level for IR only or infrared energy only. And then there's another 12 milliamp plateau or level that says I'm seeing UV only. So those are the two pre-alarm levels that the FL500 offers. I didn't actually put that into the graphic, but I wanted to just mention it, that those are there. And so if the analog input cards supports assigning flags or intermediate flags at 8 and 12, you can that is an option for every customer to consider if it makes sense. But anyway, I just wanted to quickly summarize how the analog output works on a flame detector. And this is common to most most flame detectors on the market with an analog 4 to 20 output. Now, I also I showed you this before. This is the audited coverage map from our one of our flame detectors. And so the question was, the reason I did this, I wanted to just address how we would, we got a lot of questions. How many detectors do I need and where do I put them? Well, we have to create a map. So the first thing we do is basically replicate these audited and validated coverage maps and bring them into AutoCAD or into a drawing program and then examine the coverage provided by different detector locations, different mounting angles, and also basically precursor to that is prioritizing the highest risk ignition zones in the facility that we need to cover. So with this coverage template and then a fire zone definition, highest to lowest priority, we can then answer that question. And this slide is just basically, I wanted to show that low has a certain coverage, medium it's proportionally larger because we've increased the sensitivity, and then or basically decreased the alarm level requirements, the energy level, so then high. So this is not to scale, but I just wanted to again kind of graphically illustrate this coverage changes as you increase the sensitivity setting. And then but what I've seen as a field service tech is that so often the flame detectors are not aligned, the field of view is not controlled like it should be. And so a lot of times I end up at site when I was actively doing this, changing the field of view, and I would use a laser aiming device to identify the 12 o'clock top dead center, vector of sensitivity. So I'm controlling that and not allowing that to get out into the horizon and outside of the facility. And even if it's indoors, maybe in the wintertime when everything's closed, it's not a problem. But in the summer, the doors get left open, the windows get left open. And now our detector is looking out the window to next door where they've got a campfire or some crazy thing like that. So, and in fact, talking about false alarm sources, let's talk about that. So what are the most common ones for these flame detectors? Well, in the oil and gas industry, especially places in like Alaska, West Texas, flare stacks are just out there. And those, and even though FM, validates performance of flame detectors to, 1 foot by 1 foot pan fires of liquid fuels or 32-inch tall, gaseous fuels. Hey, these flame detectors, regardless of manufacturer, they'll see a 50-foot fireball. They'll see that a mile away, possibly. I mean, 100, at least certainly 100 yards and beyond, no problem. And also on your aircraft hangar apps and any place with basically airports, you've got the possibility of a jet engine they call it a wet start, where the engine creates a fire at the afterburner or at the exhaust. Arc and gas welding, gas welding by definition, that's a fire. I mean, and even arc welding, although our detectors are tested to reject arc welding, well, the reality is, if the welder himself or herself pulls some molten steel up off the piece getting welded and it begins to burn, well, that's just like a little Bunsen burn. That's just like a little sterno stove, and so it is a fire. It's going to get detected, and it's happened. Also, truck exhaust, boiler burner fronts, gas turbine combustion sections, reactors with a combustion process, or cat cracker. They have combustion in there. The thermal signature of they call it the black body radiation energy is close to that of the temperature of a real fire. So in many cases, detectors are very good now, much better than they ever were at rejecting, identifying, and discriminating it, but they're not impervious. And especially if you had a combination of things going on, like a hot turbine or a hot reactor signature along with some lightning or a grinding nearby, now you got this combination platter of IR energy and UV energy, and you're setting the stage for things to happen. Now, corona discharge, that's a UV only source. That's from when a high voltage conductor begins to have a breakdown in insulation resistance, they can actually glow. And that corona discharge is what that glow is, and I'll leave it at that. Also, X-ray, any nuclear radiation is going to have energy that's going to be detected and sensed by a Geiger-Müller UV phototube, because they are not impervious; they are sensitive to that energy. So there's a quick rundown there. I like to talk about coverage techniques, basically coverage techniques now with these flame detectors. So this is just an example of a 3-compressor. Basically building three compressor skids, maybe a Recip engine compressor. And the most common way of protecting these types of skid-mounted equipment is to put detectors in opposing corners, looking back towards center. So we got 1, 2, and 3 all in the opposing in that corner, and then these detectors come back 4, 5, and 6 all come back in the opposite corner. So here we are using 2 detectors to cover each of these compressor skids, and we got all 5 sides covered by these 2 detectors. And so here it is efficient utilization of the field of view. We can provide a degree of discrimination on each detector. We're not, there's still going to be some in a certain location, 2 detectors might see it, but the bottom line is we've got each one covered as thoroughly as possible. Still have to look at obstructions and ducting and piping and so on, but by keeping the elevation at roughly at or just slightly above the top of that piece of equipment, we can now make sure they're accessible for maintenance purposes. And then if I'm the technician on site, I'm going to have those install locations and aim points documented in my database for future use. So if I have to take one down, I can basically, using just geographic coordinates, identify where to replace it and where to re-aim the laser aiming device, that green dot where I documented its coordinates on the floor. I can put the laser aimer back on there, put the dot back on the spot that I had documented earlier, and replicate its alignment angle. And then if we are going to drive a suppression system, a best practice here is to use the cross zone voting, where I require 2 detectors and alarm before I dump some type of water deluge or a releasing system. As far as accessories, we've got a test lamp called the Model TL105, and this allows basically on-demand alarm system response testing in your hazardous area. Maximum range with our UVIR detector is going to be about 20 feet on center, and that's with a full battery charge, with the windows clean, with the high sensitivity setting. MSIR, we'd see a maximum of 35 feet on center, again with clean windows, full charge, and everything set up properly. We also have a rain and dust guard, and I'll tell you, for every outdoor application, I recommend that accessory. That helps keep dirt, dust, contamination, off the window. We have an air curtain accessory. It does require compressed air, and it's usually used in paint spray booths, coating operations, some paper mills where they have a high level of airborne fines, that kind of thing. And then I also wanted to just talk about the this is the last slide on the flame section, and so I have in my past been given a flame map. Every project should have a map, you know, some plan that says this is how we're going to ensure we got the proper coverage we need in our high risk area, and so the point of this slide is just to share my experience in being given this map and said, so Dave, go to site, make this map into reality. Well, you got to do an audit of your site. This map, it's amazing what we can do now. But the bottom line is, some locations, when you get to site, if you see that there's a piece of steel in front of it, well, that's not going to work. And maybe the map, the drafts person, the person running the program, didn't know that that was there. And that's the reality. These are complex sites, and these photos represent that. That it's not unusual to see undocumented physical obstructions in the way of the flame detector. And same with the gas detectors as well. Or that the piece of structure where they wanted to put it, it's not. This is very, very flimsy. This is not going to work. Or a high vibration. And I was at a job site once in Canada where there was steam steam release vent was putting the flame detector in a constant state of dripping condensation. It's like, okay, guys, this is not. So again, you've got to look at it from a realistic perspective, that the map is a theoretical model. We've got to translate it. If we're going to translate this to reality, we've got to make sure it's suitable, and that our people on site can maintain these things, because I know from experience, if they can't reach the device, it won't get maintained regularly. It's just the reality. So with that, we're at 8:35 or Central Time actually. So let's take 5 minutes if that sounds good, and before we come back and talk about gas detection. So go ahead and take 5. Please come back in 5 minutes, or so at 40 minutes past the hour, if that sounds all right.
During the break, I'm going to show a couple of the tools on our website and MSAGM's website for those of you that are interested. Chris, if you could make me the presenter briefly. Okay. Collapse this. Okay, so here is there are a couple of tools here that I want to point out in case you're looking for technical information and simulation tools. This is the MSAGM website, and on their products, and I'll just go down here to the flame detector here, the FL500 UVIR. You can drill down on every product and of course get part numbers, configuration, all that sort of thing. Plus we have a simulator here. And I just want to point this out. This is a good way of visualizing the coverage beam angle for different fires. So you can click on a fuel over here and then select a sensitivity curve that you want to look at, and it will give you angles and distances and so on and so forth. So it's just a easy way if you've got some propane bullets that you're trying to protect. You can click on that and instantly get a graphic here as to what kind of coverage that detector is going to provide, and then switch it over to methane and see how that correlates with the same unit. So that's one here on the MSA website. I want to also add that we are recording this webinar for future use, and it will be posted here on the Gilson Engineering website. And it will be not only on our website, but our YouTube channel. And that will allow you to revisit and watch this webinar at any time in the future. Or if you have new people coming on board and you want to walk them through, this overview, I'll be sending out the links in a follow-up email. In general, when we put our product catalog together, you can search on different products. For example, I'll just search on flame detection right now. And there's often, there's of course data sheets, often instruction manuals, introduction videos, flame and fire detection. Here we have, you know, an intro video to the line of flame and fire detection. When we talk about gas monitoring, we also have calibration videos, intro videos, specifications, frequently asked questions, so that if you're out in the field working on one of these and you see an issue, what we have done just through our knowledge base of having, you know, our 15 guys out in the field working on these things, we just have developed a little knowledge base of frequently asked questions. Hey, I see this. What could it be? And so we've collected them here in FAQs. We also have a reference section on our website, and so if you come down here to reference and then look at, let's say, fluid and gas, we have fluid and gas properties, flammable gases and liquids with LEL tables and other technical data that you might be looking for. And we not only have those for combustion and gas, but we also have them for other things that you might be trying to measure, like level, flow, and temperature, other technical charts, all in here under the reference section of our website. So just some tools out there that can help you through what you try to do on a daily basis. So I'll close all this out, and we can go back to Dave's screen. Dave, are you back?
I am back.
All right, good. All right, well then
let's
turn
just
it
make
back
sure
over
I'm
to
in
you.
Okay.
We are in your, we need to get back to your presentation screen.
Okay, gotcha. Yeah. Okay, so you're seeing my full screen, right? You're seeing the presenter screen?
I'm seeing your presenter screen with the notes on the side. Yeah, there you go. All right.
All right, well, welcome back, everybody. We're gonna switch gears now and talk about fixed gas detection. And the point of this slide, we just talk at a high level. I'm not going to spend a whole lot of time on any one of these, but I want to just mention them out there, or mention what's out there. And starting in the lower right, going clockwise, we'll talk a little bit about combustible gas point monitoring. We'll talk about toxic gas point monitoring. I have a slide or two on the ultrasonic leak detection instrument and the open path as well. So yeah, it won't take long. It won't be long. I'm just going to do a high-level discussion, but let's start off with combustible. So, question for the audience, for everyone on the call today. Can you guess what the first type of combustible gas detector ever used was? And I'm not going to wait for an answer, but you might be surprised. It was a candle on a stick. And that's, you know, what? A candle on a stick? What do you mean? Well, in the coal mining, back in the 18th and 19th century, coal mining basically in Europe, miners had noticed that the candles they were using to see underground, while they were digging out this coal by hand, these candles burned more brightly just before the methane explosion occurred. And after killing themselves and blowing themselves up many times, they realized, okay, we can't proceed with mining activities until we clear the methane pocket. Well, how do we do that? Well, we're going to draw straws, I guess. And this poor chap on the left drew the short straw. So what they would do would be cover themselves in wet burlap and put the candle on a stick and thrust it into the area where they saw the candle burning more brightly. And what I was reading was that their survival rate was roughly 50-50. Eventually, some smart person realized, well, if we take that candle on a stick and put it inside of basically a container and use maybe some gauze as a flame arrestor to prevent it from, you know, the passage of the gas, the overt exposure to the gas right away, that we could maybe see a change in that flame from the methane presence without causing explosion. So wow, what a breakthrough, right? A handheld flame lamp that prevented lives from being lost. Well, fast forward to today. Guess what's using the same theory of operation as that candle? It's the catalytic bead gas sensor, right? The heat of combustion basically is the theory, is the same concept as that candle, where instead of using a candle though, or even a little flame in a flame lamp, the Cat bead sensor uses a pair of resistive coated hot wire beads. One is an active bead, and this is where the actual gas is catalyzed, the molecules are catalyzed. And then there's a reference bead or a compensation bead. And this is passive. It's coated with glass. But these beads have the same resistance, electrical resistance in clean air. And so they're a balanced circuit in clean air. But when vapors permeate through the flame arrestor around that Wheatstone bridge circuit, right, the molecules of gas contact the active bead, which creates heat, which changes the resistance of the circuit proportional to the concentration of vapor in the measurement chamber. And that measurement chamber is shown in the lower right-hand corner. And so you got to have a flame arrestor. That's what prevents these hot wire beads from actually igniting the gas, should there be, flammable gas there. So, and they're sometimes referred to as a pellister, or which is a word, a compilation of the words pellet resistor. So in England, they call it a pellister. But what's really neat about this technology is it's fundamentally accurate without any microprocessor, right? Don't need anything to process the signal. It's a millivolt signal coming out of that circuit, and that's up in the upper right-hand corner shown. That's fundamentally accurate. In fact, the ISA standard, requires manufacturers like MSA and anyone to, if that's going to be approved to the standard, which they have, it's got to be plus or minus accurate, plus or minus 3% of applied gas concentration from 0 to mid-scale, and then plus or minus 5% of applied gas from mid-scale to full scale. So it's really amazing that these devices are that accurate. It can be that accurate, and they have a wide operating temperature range. In fact, if it's a high temp app where you're really above the temperature rating of your 32-bit processors, this is a great way to go. And they, but they are destructive, right? So they have to burn the gas to measure it. And so there's a failure mode. I haven't put a slide on this, but bottom line, even though they might last 3 to 5 years in a nice clean site, if that site has airborne, well, the number one poison is silicon. So a maintenance person sealing up windows or fixtures with RTV adhesive silicone sealant, well, guess what happens when those molecules contact those hot wire filaments? They coat it like with an impervious coating of saran wrap. And so even though the resistance of the bridge is the same, it's not until the technician goes out and applies the CalGas on a routine basis and goes, oh, holy mackerel, this thing is not responding, or it's very low response. So their poisoning can happen, which set the stage for another technology that doesn't have that same weakness, and that's the NDIR, or non-dispersive infrared. This is a non-destructive measurement. It's an optical measurement of gas. What are the components? I got those shown across the bottom. An infrared lamp on the left. You got a measurement chamber in the middle where the lamp energy shines through that measurement chamber. And then you have the electronic section on the right, and that includes the sensors. We have an active sensor called the measurement sensor. I've shown that with the red bandpass filter, and a reference sensor that is this measuring an adjacent frequency of light not absorbed by hydrocarbon molecules. And basically, those signals go into a microprocessor where a ratio is calculated along with some other algorithm parameters defined in the Beer-Lambert law. We end up with a 4 to 20 milliamp signal proportional to the gas concentration in the measurement chamber. And I've got a little animation to show you that. Right? So these guys are located in a site, and then the whole premise is that the vapor of interest is going to basically impinge and fill up in that measurement chamber and absorb that frequency of light on the active measurement band, and then that enables detection to occur. Now, the strength here is, again, where the Cat bead sensor, which is destructive, may last 3 to 5 years, maybe longer. You can expect this type of technology, because it's not having to burn anything, create heat. As long as you're not vibrating it to death, it should last 10 years and beyond. They can be packaged in 2 different ways. They can be packaged in a point infrared instrument, and I've got some examples in the upper right-hand corner there. And these are point detectors that are placed, using the same thought process, the same evaluation principles as Cat bead or toxic point detectors. But then you've also got this open path infrared instrument configuration shown across the bottom, where essentially what's happened is our engineers have taken the lamp out of the point infrared instrument and put it into a module called the transmitter. It also and stepped it up. It's a much more powerful, lamp type. It's a xenon flash lamp rather than an incandescent lamp. But now we've got an instrument that can be used to monitor a perimeter of up to 100 meters plus in total weight and total physical distance, and any hydrocarbon cloud basically migrating into that beam of light will absorb the same frequency just like the point IR detector, and the receiver module will measure that absorption and provide an output that represents the total molecular hydrocarbon content in the beam. And what's the benefit here? This thing sees a gas leak that your point detectors very well may have missed, because again, point detector depends on impingement. This guy, you got 100-meter basically light fence line of light, and much greater opportunities to detect the gas. So this is kind of a common sense. I just talked about most of this already. I won't spend a lot of time, but cat beads have, here's a quick comparison head to head. They have a lower initial cost. So many customers say, hey, I like that. It doesn't cost me. That's true. But you're buying into regular calibration, because as I talked about, they're not fail-safe. Poisons exist. They have to be calibrated to check that they're available to detect and perform to the expectation. They require some air. In fact, they're not suitable for low oxygen conditions. It is a reaction that requires the principle of the heat combustion requires air for accuracy. And again, 3 to 5 years is pretty typical life expectancy on these guys, because they are a destructive measurement. It's like the light bulb is on, they're always energized. Now, point IR detectors have a higher initial cost, right? They're a little more expensive, not much, but they don't detect hydrogen. Where that's the other, I didn't talk about that initially, but cat beads, where they're really one gas that they are required to for all purposes, or for gas detectors, hydrogen. You have to have a cat bead for hydrogen. But point IR, they're great for your C1 through C7 hydrocarbons, but they can't detect hydrogen. They are fail-safe, though. I mean, fail-safe in the internal failure mode sense. They don't record the same level of calibration. They don't have any poisoning impact. They don't care about oxygen. They don't need oxygen for their measurement. They can be very fast speed of response, and of course, and ours has a 10-year warranty. But let me say one thing. Regardless of technology, cat bead or point IR, the technicians on site responsible for managing the system need to do a visual walkthrough, because if the gas path is blocked from something external, and one site I went to, the painters had left bread bags taped around the gas detector. So, and no instrument, regardless of manufacturer, is going to be able to sense that I got a piece of tape or a bread bag wrapped around the sensor, around the instrument. So it's that visual check. Just like I talked about flame detection, it's the same thing here. We have got the same: green is good, red is alarm, yellow is trouble. Well, so part of that daily walkabout is to look for the green LEDs and make sure on all your flaming gas, and make sure there's not a bread bag wrapped around the instrument. So moving on to toxic gas detection, similarly to our combustibles, we have two types of toxic detection we can offer, and on the market, I should say. One is the point type, the traditional point type, similar to the cat bead and the point IR, and we also have a laser-based toxic device, and that is it's specific to, and it's called the Sensiana. I've got a slide coming up on that, but this is just a high-level summary, and I'll talk about electrochemical toxics first. So what is an electrochemical toxic gas sensor? Well, think of it as a micro fuel cell. And what do you mean, like a battery? And the answer is yes. Difference being here, I mean, so the construction is shown there on the left. That you've got a cavity, and in the cavity is electrolyte, and also in that cavity is electrodes, right? We have a sensing electrode and a reference electrode, but instead of being a sealed battery, this electrochemical sensor has a permeable membrane on the face of it. And what does that permeable membrane do? It allows vapors to permeate through the membrane and into the cavity. And what happens in the cavity when the specific gas or the analyte to be measured permeates through there? It creates a microcurrent flow between the electrodes. And so our engineers vary the electrolytic fluid and the electrode materials to provide specific response to different gases. So even though they're all built in a very similar way, it's the chemistry within that is very specialized to provide that high accuracy measurement capability to the different gases shown in the lower right-hand corner. H2S, carbon monoxide, we have chlorine, we have a full range of gases. I didn't list them all, but I wanted, because this is the point here, just talk about how they work, but they are diffusion based. They have to be placed where the vapor can contact the sensor and then permeate through that membrane and into that cavity where the microcurrent flow occurs. And then the transmitter module converts that to a milliamp signal and usually has a local onboard display as shown in the upper right. But then also we would route that signal to a logic solver, a gas controller, to provide audio visual alarms and then some notification. And obviously we want to also log that data. We want to be aware of how often we're having alarms, that kind of thing. So that's a brief rundown on electrochemical gas sensors. There's some pretty neat things happening here I'm going to talk about coming up to briefly on technology that actually improves the availability on this and reduces some of the calibration requirements and cost of ownership. The other toxic gas sensor I talked about was the laser open path, and ours is called the Sensient. And this basically the photos there on the right, and it's a ppm capable open path system. Its strength really is toxic. It can do flammables, but its strength is the toxics. And on the left side, I got a listing here. We got up to 120 meters. This system can detect ammonia vapors, hydrogen fluoride vapors. It can also sense carbon dioxide, hydrogen chloride, and hydrogen sulfide gases up to 60 meters in length. It can do flammables out to 200 meters. Again, it strength owes these toxics, and we've got a dual range capable device as well. And I'm not going to spend a lot of time on this. In fact, it's the only slide I have, but I wanted to mention it to our audience today, as well as another technology here, and this is Acoustic. So this is a microphone-based gas detector, and it's kind of the early warning. It's a layer protection. Consider it the early warning system. Where is it really optimal? It's really optimal for high pressure, windy outdoor settings where the wind is always blowing, and you could put a line of sight, you could put a point detector, but we're just not 100% sure that because of the windy situation here that we've got we're going to sense that gas. So it is required to, a prerequisite to using this is that your hazard is pressurized. It's a pressurized gas leak. It is not capable on liquid spills where you just have a pool of flammable. It's not going to sense those. In fact, here's the strengths and the limitations. It's very fast, so it can sense a pressurized gas leak even upwind of it by listening for the ultrasonic acoustic signature of that hiss, if you will, of gas. It's great for outdoor ventilated areas, explosion hazard areas, but as I mentioned, it will not sense vapors from a liquid spill or a low pressure leak, and it can't differentiate compressed air leaks from actual flammable or dangerous gas leaks. So they have that same signature. So, but again, where those areas where it's a tough situation and where we see most of them installed is offshore oil platforms in the North Sea and in windy areas like that. From the service technician perspective, this is one of the most useful accessories for any point gas system, and that's a sensor separation kit, a remote SEP kit. And why? Because this allows the end user to put that sensor where it's going to be optimal for early leak detection. That might be high for methane, lighter than air gases, or hydrogen. It might be low for your heavier than air gas liquids, or gasoline or heptane or some other heavy vapor. But then keep that transmitter at eye level for easy viewing and accessibility. So I just showed it with our X5000 there connected to a sensor, but all of our sensors support this remote sensor capability, and I really recommend that because that way too you can have a nice row of transmitters, each with a tag identifying and you have a nice little identification tag, and again, it's just a real slick way to do it. And in fact, I want to take a minute to talk about these transmitters. They might be of interest to the audience. We've got the S5000 here on the left side of the photo, and then on the X5000 on the right. They're very similar in capability, a little bit different packaging. And we can do, I'm not doing a deep dive into this, but I just wanted to show you the two options that are out there. They both have got dual sensor capability. So you can have a combustible and a toxic, or two combustibles. on the same transmitter, and it really helps on the reduce the cost of ownership. The installation costs are less, and so on. And they are both touch screens. You don't need to have a magnet. They both communicate via HART as well as Bluetooth, if that's of interest. If someone's got a Bluetooth tablet, you can actually now establish comms with these transmitters and not have to actually be right up to them, right next to them. So I'll do let's see, a little quick. Yeah, no tools required. They have touch buttons, so it's really neat that you can put your you can just touch the glass. You don't need a magnet to navigate the setup or the diagnostic capability. You've got at a glance. We talked about the red, the green, the yellow. For normal and alarm and trouble. Well, you both support that. And then the X5000, right, that's got these really bright organic LEDs. So if it's a benefit to any customer to have a super bright LED, man, that when it turns red, you can see this sucker a long ways away. That's a benefit of that guy. Now on the S5000 on the left, here the housing is a little different because our designers wanted to make it easy for a customer with legacy general monitors, gas detectors to be able to use the same footprint with this guy. So he's a much easier upgrade if there's existing infrastructure on site with our legacy gas detectors. The S5000 supports that same mounting footprint. And also, I think Adriana told me the temperature rating on the S5000 is a little better. So it's a little higher temperature, or maybe lower. I think it's just a little better temperature ratings on it. I'll have to validate that, but I remember her telling me that. They both support dual gas capability, right? So we can have a toxic, a cat bead, a point IR, and then you can set them up different ways, right? This is on the lower left. I've got one. You can have both sensors close coupled, or you can have one sensor on the transmitter and one remote, or you can have both sensors remote and run it back into the transmitter. So I just wanted to show those options out there. Yeah, and this is, I already talked about this. The alarm is really what the one thing with this slide, it doesn't show you how bright those things are. I'd like to have show you how bright it really is. And then the Bluetooth is cool because now, if it's acceptable, not all sites it's acceptable, but now using some type of either iPhone or a phone or a tablet, you can get all the information you used to get. What you had to couple up with a HART field communicator. Got a few screenshots. You can calibrate. You can set it up. You can get a cal report. This is what these three screens just show. The calibration type, 0 or full. Which sensor are we going to calibrate? You have green checks as you proceed through the calibration process, and when you get all done, you got a cal report. And as I said, it really makes life easy, especially if it's a remote site. And in some places, I know that outdoor sites, some of the technicians don't even get out of the pickup trucks to check their devices, and especially if they don't remember when they last did it. Well, now you can make communication with the devices, and it'll give you a report on when I last calibrated you. So that's pretty cool. Another cool thing is this, we've got two new basically built-in diagnostic features in these transmitters. I'm not going to spend a lot of time on them, but they're all under the TrueCal basically label. But really, when we're going to do a deep dive here, one is diffusion supervision, and one is adaptive environmental compensation, or just AEC. So what are these things, and why are they cool? Well, so in many sites, right, you got a lot of airborne contamination, especially outside. You got stuff that can block the sensor face. And so what we've done with a few of our Excel sensors is we put a little speaker in there, a little tiny speaker in the sensor body itself. And that speaker sends out a little tone. And there's a microphone on the other side of it. And you can see it right there. I got a speaker on the left, a measurement microphone on the right. When the sensor's not blocked, the microphone gets that tone, can listen to that tone and get a nice clear, base signal level on that tone, and everything is good. But should there be some frozen ice or one of those mud daub or something's put some junk up in that opening of that sensor, which again, normally you'd hope that your technicians doing their visual walkthrough, you'll catch that, but we know from experience they don't always catch everything. So this is a built-in diagnostic. If the sensor opening is blocked and this detector can't do its job, not because it's failed internally, but there's something external blocking it, now this diffusion supervision will create a fault and let the technicians know on site we've got a problem with that instrument's capability to sense that gas. So no one else has got this. It's a very cool thing, and it does it all the time. So you can just count on this device to always monitor itself. The other really neat breakthrough on these sensors is a pulse check. So those little batteries I talked about, little micro fuel cells, right? They create a signal level in response to basically a electronic, basically, talked about the microcurrent. Well, the pulse check is a built-in diagnostic that essentially looks at the pulse level or the electric current generated during the calibration process and is able to map that internally and essentially recreate that level automatically. And so it's basically, once it's mapped and identified the internal signal, the electronic signal level that instrument created during its last full good calibration, now every 6 hours, the microprocessor stimulates that sensor with the same level of energy that the cell created during cal. And basically, if it's good, it says, hey, we just checked ourself with a pulse check, and I stimulated it with a similar response, and we're spot on. But if there's a little bit of degradation, the sensor's been working and maybe it got exposed to some contaminants or something, it'll automatically respan that sensor to match the last good calibration. And so what's the benefit for everyone in the audience? What's the benefit for users? It lengthens the amount of time in between routine calibrations. So it is amazing, and to the point where it would be possible to reduce calibrations on these devices down to once a year, which is incredible. I don't want to say that's the case in all situations, but it's a possibility. What it is diagnostic that ensures reliability, availability of the instrument all the time. So quick summary, I'm almost done here on this. AEC is what we just talked about. That is the ability to check itself once every 6 hours and adjust it automatically if it needs to. And then diffusion supervision is the little speaker and the microphone checking if the inlet's blocked. And both of these basically reduce the cost of ownership while increasing your safety. So it's pretty cool. All right. So we're wrapping up. We're getting close to the end here. I wanted to talk about installation, operation, and maintenance. So if I'm working for you as your installer, I'm going to make sure, or if I'm managing a project and I'm working with installers, I'm going to get with these installers and say, I want to make sure they understand what they're doing, that we have a map, and that they're going to be responsible for ensuring our system is installed as per the map, or we're going to balance reality with the map. And I want to make sure they're qualified people, that they're aware and informed what they're doing. I've seen the opposite, and it's not a good result. So we have to create awareness and informed installation people. I want them to know if this can be a ground fault monitored system or not, because if they don't make terminations properly, that can create ground faults. And I don't know if you ever had to troubleshoot ground faults. It's not fun. Cable shielding, terminations, conduit seals, breathers, and drains. I want to talk about that with them. I want to talk about flex conduit on the flame detectors. I want to talk about the power supply, make sure it's sized properly. And this is more on the design side. But at installation, we're the last line of defense on a properly engineered system. So I want to make sure all that is good. I want field tags and visible for my operators and my maintenance people. And I'm going to make sure we got a quick reference spreadsheet where I've got tags listed, installation locations, document, traceable coordinates. I talked about that. Sensitivity, all the settings, the config settings, time delay, sensitivity, latching, config, cal gas. What kind, is this a methane sensor or propane sensor? So I got this database, it's in Excel, and that is just a wonderful tool, especially for the team who owns it after we leave the commissioning site. Ops and maintenance, I talked about this daily walkthrough or weekly walkthrough where our people look for green LEDs on the devices. We're looking for no obstructions. We're looking for proper installation and alignment angles. And everything looks good. We don't have something you can. Once a technician becomes experienced, they can tell it in a glance. There's something not right there. And then also our key inspection points, and then the go and no go criteria for our new hands. I like quick reference maintenance guidance too. So we have a training. I'll talk about this more in the training topics, but identify the types, the configurations. Again, have some basic knowledge that we share in some quick reference guidance, spare parts as well, how I get a spare sensor, if we want to do it, what's our routine on testing and so on. And this translates to a logbook. Fire and gas system should have a logbook. This actually complies with ANSI ISA and NFPA 72, where we got, again, all of our faults, all of our alarms, our tests, our cleaning activities, logged by tag, device tag, date, and who. I love the new HMIs on some of the new systems, because now, in the old days where we had a 3-ring notebook or a spiral notebook, we can now have an automated graphic user interface from the logic solver to if we lose the logbook, now we got a copy automatically populated by the logic solver, which I really like. But gas calibrations, again, by changing some of the newer things now, actually help simplify and optimize the calibration ownership, the responsibility that's out there. We have to have cleaning routine, cleaning, how often do we clean, defined, and then testing as well. And so then this is the last slide I have, and this is the training piece. And I was a trainer, I still am a trainer. So we should have a training program for our technicians and our process engineers, everyone involved with the system, how to perform a visual inspection, document the findings, how to identify when and where a fire or fault has occurred, as well as a gas alarm, how to bypass the system if we need to do some work on it, how to calibrate a detector, how to clean the optics of a detector, how to find the logbook and schematics, how to troubleshoot a basic fault or trouble condition, how to perform a response test using a test lamp, how to reset or power up or power down that system, and who do I call if I need help. Well, that actually brings us to the end, and I hope you found it useful. Definitely like to open up some questions if there are any out there. Again, it's been great being here. I hope you found it interesting and informative.
We have one question, is IR more stable than cat bead? If so, does it mean that it doesn't have to be calibrated as often as the cat bead? I thought you addressed that, but maybe touch on that.
Yeah, briefly. Yeah, I would say this, that in certain applications, IR, point infrared gas detectors, are very beneficial. And primarily the point is that they just, yeah, they're more stable. They are less likely to be impacted from foreign, vapors and liquid vapors, gases and vapors. They're more resistant to poisoning. So the degradation of the sensing capability is much less sensitive, because the cat bead, it's a non-selective device. It simply tries to catalyze or burn anything that contacts it. So what is really bad? H2S vapors are bad for cat beads. I talked about the silicone, the poisoning, where you actually coat the bead with this impervious material. And so the bottom line is, and acid vapors as well, vapors that polymerize when they're heated, those all can adversely impact, cat beads. So point IR, non-destructive technology, it is more resistant to fundamental poisoning. They're not impervious, but they're more resistant.
Okay. Looking at the chat log, I don't see any other questions. Anybody have anything they want to ask Dave before we break? All right, seeing none, then we will